Hi, this is AS Paper 2 exam review. First question is looking at a PV equals nRT question. Remember, the big thing about this one are the units are not quite what you think they are. Pressure is in pascals and V is in meters cubed. So we want N. Okay, just making the change here to the units. So volume, we go from centimeters cubed to meters cubed. Well, that should be meters cubed. And grams. Okay, so we can put the numbers in. So we've got 102 times 10 to the 3 pascals times by the volume, which is 72 times 10 to the minus 6 meters cubed, over R, which they give you 8.31, times by temperature, which they weirdly give you in Kelvin. So bash that into the calculator. Just working it out. So 2.37 times 10 to the minus 3 moles. What else have they given you? The MR equals the mass over moles. So 0.194 over 2.37 times 10 to the minus 3. Okay, does it give us a sensible answer? That's the big thing, really. Okay, key point here, appropriate significant figures. Everything is in 3 sig fig. Oh, no, it isn't. 2 sig fig. Yeah, because look at the volume. 72. Okay, next one is we're trying to work out the empirical formula and work out the molecular formula from that. So we take the percentages. We have to work out that there is 16.3% hydrogen. And we work out the moles. So those are the moles. You need to find the simplest ratio. So 6.973 and 16.3 are the moles. To find the simplest ratio, divide by the smallest, which is 6.973. So we've got a 1 to... that's not going to be a whole number, is it? 2.34. So if we times them by 3, that should give us a ratio of 3 to 7. Okay, so there's our empirical formula. And if we work out the MR of that, it's 43, so which is half of the, so it's C6H14. Right, okay, so mean bond enthalpy is the energy required to break 1 mole of bonds. Those are covalent bonds, really. Averaged. Now, strictly speaking, that should be in the gaseous phase as well. but that wasn't in the mark scheme. But it should be gaseous substances there. So why it's not required in this mark scheme is something you should remember for the future, that it's 1 mole of a gaseous substance as well. 1 mole of bonds in a gaseous form, averaged over different molecules. But they were only requiring for this one, those 2 points. Standard enthalpy formation, enthalpy change when 1 mole of substance, compound, is formed from its elements. Under standard conditions, with the reactants and products in their standard states. Right, so marks there, 1 mole of compound from its elements, and then standard stuff. Okay, next question is looking at bond enthalpies. So delta H equals bonds broken, sum of the bonds broken, over, so minus the sum of the bonds formed. So they'll expect you to lay it out, work out what they got. So we've got 4 times the nitrogen-hydrogen bond, so that's 388. We've got 1 times the nitrogen-nitrogen, which is 163. And we've got 4 times the OH bond, which is 463. Right, well, I've gone for that one. 2 times the OO bond, which is 146. And 4 times the 463. I don't know why I haven't put the actual value of the OO bond. That's silly of me. And then it's minus bonds formed. So we've got nitrogen-nitrogen triple bond, and then 8 times the OH bonds there. Got to try and work out each one. So you've got to work out the bonds formed and the bonds broken, and the statement. What's this next one? Standard enthalpy of formation are given below. Now you can use the triangles if you want to. Probably better actually. And why is it 0 for nitrogen? Because nitrogen gas is an element, and it's defined as 0 from the elements, because you're making an element from its elements, which doesn't really make sense. Next one, use the delta HF values in the table to calculate enthalpy change of the reaction. So this is what I was saying. It's pretty good actually to draw the cycle, but you can use the equation. They don't mind these days, either ones or the two. So to a delta HF formation data, it's products minus reactants. And so you just make sure you get the right values there. So products, there's nothing for the nitrogen, we just said that. There's 4 times the water, so it should be 4 times minus 242. And then you're minusing 75. And then you're minusing 2 lots of hydrogen peroxide, so minus 2 times minus, 2 times minus 3, 133. Okay, it's important, right? You start to write out your equation, you put your numbers in to show you're working out, and then you put your answer. Obviously, if you get the answer, then you automatically get the 3 marks, or the 4 marks. No, it's 3 for this bit. You automatically get 3 marks. But if you don't get the right answer, then you got to go back and look for different the steps along the way. Oops, why is it flipped on its side? No, it's gone back. Why is it the two values aren't exactly the same? Well, the mean values are not exact values. Right, so this looks like a calorimetry question. Q equals MC delta T. It's always worth putting that down. You're going to have to work out the difference in the amount of fuel used and the difference in the temperature change. So the first thing to do is to answer that question, which says the equation for the complete combustion of leaf alcohol. There's the equation for it. And then B says use the results from the table to calculate the value for the enthalpy of combustion. So it's worth writing out the equation Q equals MC delta T. 50 grams of water. So we can use the density of water as 1 gram per centimetre cubed, 1 gram per milliliter. But actually that's a mass there, so we can just put 50 in there. 50 times 4.2 times by the temperature change, which you should have worked out as 20.1. And that should give you your answer in joules. So let me just type this out. So 4,200 joules. Now we need to convert that into kilojoules. So we'll divide that by 1,000. So 4.2009 kilojoules. And then we do need to divide it by the number of moles of fuel. So we need to work out the number of moles of fuels. Now we've got a mass of fuel. So our mass of fuel equals 0.54 grams, and we divide it by the relative formula mass. We're going to need to work that out because what is it? C6H11OH. What does that equal? So divide by, that gives us 0.0005. Oh, it's 100, I see. Yeah. Okay, that makes sense. So the RFM is 100, so it's 0.54 grams divided by 100 equals 0.0054 moles. And divide your answer by that. And then we need to sort of work out where the marks are. Obviously, when you do these calculations, if you get the right answer at the end, as I said before, you can just allocate the marks. But, oh, wait a minute, that needs to be minus. That's a minus the enthalpy change there, because it's exothermic. That's minus at 7.78 kilojoules per mole. Am I going to change it? No, I haven't changed it. Why is that? Yeah, just be careful. It needs to be minus that value. That's silly of me. State how to answer your is likely to differ from the value quoted yes, there's going to be a lot of heat loss. So therefore, it's not going to be accurate. But what does that mean in terms of your actual answer? Your answer is going to be less negative than expected. Yeah, well, there you go. I've gone and changed it back there now. So it was minus 778. 5 grams of sample was used in the experiment. How could you measure the mass of water using balance? Well, using the fact that the density of water is 1 gram per milliliter or centimeter cube, you can measure it accurately. Fairly straightforward. Right, next question. Okay, do we need to name this molecule here? So there's 1, 2, 3, 4, 5 in the longest chain, but there's 3 methyl groups. So we're going to call it 223. No, wait a minute. That's 224. 224, that's wrong. I've written that down wrongly. It should be 224 trimethyl pentane. Oh, it's flipped again. Sorry about that. A should be 224. How would you separate them? Fractional distillation. What does it say? Outline the technique that separates, how this technique separates it. Okay, so the isooctane is going to have a different boiling point, so because it's going to boil off first, it's going to have a lower boiling point. Well, it says that actually, 99. So it boils off first, and then it's condensed. Complete combustion of isooctane. So it forms carbon dioxide and water. There's going to be 8 carbon dioxides, 9 waters. Divide the number of hydrogen by 2. Put those all together. So it's 4.5. Looks like 12.5. Right, it says here, explaining general terms how a catalyst works. Well, it provides an alternative mechanism with a lower activation energy. So a lower activation energy using a different mechanism. That's how it works. 1 mark for each point. No matter which order. Carbon monoxide is produced when incomplete combustion has taken place in the engine. Nitrogen monoxide is another pollutant produced in car engines. Write an equation to show how these pollutants in the catalytic converter. So you want something safe, so you want CO2 and you want N2 there. Platinum, palladium, rhodium are metals used in the catalytic converters. A thin layer of metal is used on a honeycomb. Explain why a thin metal is used in this way. So you need to increase the surface area, make it as big as possible, and that means you can use less metal, because the metals are very, very expensive. I mean, yes, they can be recycled, but they're still very expensive. So here we are. We need to identify this show that it's unsaturated. Well, you need to use bromine water, and it will decolorize, so it go from orange to colorless. So it decolorizes the orange bromine water. Right, next question. So this is a standard enthalpy of combustion type question. Can't quite see it here. State the meaning of the term standard enthalpy of combustion. The enthalpy change when 1 mole of substance is burned completely in excess oxygen under standard conditions, under standard states. Yeah, you need standard conditions and standard states. Right, so here we are. There's a reaction. It happens to be a formation reaction. They want you to work out the energy of this formation reaction using the data below. You can use a triangle, where remember the arrows on this one are going down, or you can use the equation. Either way, you've got to state which one you're using and how you're using it. But remember, if you're using delta HC data, it's got to be reactants minus products, not the other way around. So that's one part of the question. Yeah, so there's the arrows, what they would look like, and there's the route you take. So that's how you get reactants minus products. So you need to put them down. So it's 3 times 394 minus 394. And 4 times minus 286. Obviously, burning oxygen is a meaningless concept. Minus, there's the totals on that side, minus 2010. So it's going to equal minus 2326 plus 2010. And that should give you minus was it minus 216? Oh, 316, sorry. Right, here's a bond enthalpy question. So for the complete combustion of use some bond enthalpies. So bonds of reactants minus bonds of products. Once again, that needs to be stated. And then you just list them really. So how many CH1s are there? 1, 2, 3. You've got 7. 7 times 4, 1, 2. How many CCs are there? Oh no, that's what we have to do. We have to find the oh, I see. Yeah. So they give you that value there is 1893, and then you list all the bonds of the reactants and then the bonds of the products. Seven times 412. Then you've got a CO bond, so plus 36. And you've got an OH bond, which is 463. And then you've got 4.5 times the O bond, which is 496. So 4.5 times 496. And then you take away 6 lots of the CC double bond. So that's 805. And 8 times, take away 8 times the OH bond, which is 463. Okay, so 1 mark for the start bit of the question where you state what you want to put down. 1 mark for the showing the calculation. So all that's happened there is resolved all those numbers on the right hand side. Move that over. Next step. So 2593 minus 1893. 2595 minus 1893 equals 2 lots of the CC bond. So divide that by 2. So that equals 702. Is it positive? Yes. Is it a sensible answer? Yeah. Yep. Okay, so 1 mark for the statement, 1 for the calculation. So question 6, draw the structure of Z-methyl pentateuine. So the Z means that the two big groups are on the same side, on the same, and the big group on the left is the methyl, and the big group on the right is the ethyl. So there it is as a sort of a hybrid structure, and then there's the skeletal. Okay, name and outline the mechanism for the formation of 3-bromo 3-methyl pentane from the reaction. So it's electrophilic addition. So it's going from an unsaturated to saturated. And we're adding a bromine, and we're reacting with hydrogen bromide. So we've gone to the bottom down there, so we're going to draw the mechanism down there. Remember, the electrons come from the electron-rich area, so that's what the curly arrow shows. There's a permanent dipole on the hydrogen bromide. And so the hydrogen goes on first, leaving a carbocation, and then the bromide attacks the carbocation. The next part of it says, explain why more 3-bromo 3-methyl pentane is formed in this reaction than the 2-bromo. Oh, it's to do with the major and minor products, because this is an asymmetrical alkene, and the one that proceeds via the more stable carbocation you get more of. The one with more stable carbocation is the well, remember, stability goes, the most stable is tertiary carbocations. There's 3 carbon groups surrounding the carbocation. Then it goes down to 2 secondary carbocation. That's 2 alkyl groups or carbon groups around the carbocation. And then lastly, the least stable one is a primary one, where there's only 1. So once you've done the mechanism, it's then about saying that the secondary carbocation forms 2-bromo 3-methyl. There should be an L there. And secondary carbocation is less stable than the tertiary carbocation. Right, next question. Propane 1,2-diol has a structure of that. It's used to make a polyester. Okay, draw the skeletal formula of propane 1,2-diol. There's propane. There's the diols going on. Write an equation for the oxidation reaction of propane 1,2-diol under reflux using O to represent the oxidizing agent. So you're going to get a carboxylic acid on one end and a ketone in the middle. So you're going to have to add an oxygen to make the carboxylic acid, and also you're making water, so you're going to need to think about those, how much oxygen you're going to need to make water. So let's draw the structure. So we've lost one, so we're making 2 waters. So therefore we need an oxygen for the carboxylic acid and 2 oxygens for the waters. Right, draw a label diagram to show how the apparatus is set up for reflux. So you're going to have the reflux, the Liebig condenser vertically, with the water coming in at the bottom in the jacket, and water going out at the top, and it has to be open. You don't plug it at the top. So first of all, the condenser needs to be vertical. The flask directly underneath it needs to be open. You need some sort of heating mantle or flame. Flame would be difficult because it's flammable. It's a flammable substance. So the vertical condenser. So vertically above. Right, okay. There's only 2 marks there. Right, where do you add anti-bumping granules? Anti-bumping granules means that you've got smaller bubbles forming. So you don't get it spitting out substances. Draw the structure of the different organic products formed when the acidified potassium is not in excess. So you've got a different combination. Sometimes you can have the carboxylic acid forming the aldehyde, or staying as the alcohol, or you can have the second alcohol, the secondary alcohol, staying as an alcohol and not going into a ketone. So the first example here, the secondary alcohol goes into a ketone, but the primary alcohol only goes to an aldehyde. This example here, we've got an aldehyde forming from the primary alcohol, but the secondary alcohol never got oxidized to a ketone. So this example, the third example here is you got that's a carboxylic acid and the secondary alcohol as staying as an alcohol. So that line there is actually an O. And the last one, whereby the primary alcohol stays as an alcohol and the secondary alcohol gets oxidized. Any one of those combinations. Right, so what we've got here, nucleophilic substitution. It's going to be 1 mark. And then the mechanism, remember nucleophilic substitution is very, very, very simple. So remember that the Br is more electronegative, so that's going to be a delta negative, and the carbon it's attached to is going to be delta positive. That's the wrong arrow. That's more like it. And then it knocks the pair of electrons onto the bromine. It's important where the arrows go. So next one is a calculation here. And what we're looking for is the percentage yield. So first step here is to work out we've got 2 centimeters cubed. So we're going to work out the mass of the 1-bromo-3-methyl-propane, and that allows us to work out the number of moles. We can divide that by the relative mass, which is 136.9. That should give us a number of the moles of the 1-bromo-3-methyl-propane. Okay, so that's what we should have got if 100% conversion. So if we've got that many moles of the starting reagent, that must mean we've got that many moles of the product. So if we times that number of moles by the relative mass of the product, 74, we should get the mass of the product. So the expected mass of the product was 1.36 grams. So we take the actual over theoretical times by 100. But remember, we've got to convert the milligrams into grams. So that's 0.895 divided by 1.36 times by 100 gives us a percentage yield of 65.7%. That's 3 marks if you got that. And working backwards, if you didn't get that, you need to work out the mass of the expected and the moles of the original one. Okay, so what we've got, hot concentrated ethanolic potassium hydroxide. So we've got a elimination reaction going on here. So we're going to make so the name of the product, methylpropene. Oh, wait a minute. Secondary alcohol. Okay, so what we're looking for, how we're going to show if it's secondary, the product is a... Okay. Right, there's no OH, first of all, and we've got a CC. So that's how we can work out the two. And we just try to explain that because there's a peak at around about 1700, that's characteristic of the carbonyl, so therefore it must be butanone, and there's no OH peak. Oh, I seem to have missed that previous question, that mechanism. Okay, so draw the displayed formula of alcohol C4H9OH, which is resistant to oxidation by acidified potassium, but so it has to be a tertiary alcohol. So you have to draw it as a tertiary alcohol because it doesn't oxidize. Remember, tertiary alcohols don't oxidize. Anyway, I put the C in the wrong place. Yep, there it is. It's a displayed formula, so you've got to show all the bonds. A common mistake. People just sort of abbreviated formula.